first chapter of this course is chapter 1, which is about propositional logic and set theory. So that, as you clearly observe here, this chapter is containing two related portions, which are the first part of this chapter is about propositional logic, and the second part of the chapter is about set theory. So today we'll see the first part of this chapter, which is about propositional logic, and the first subtopic under this topic will be this one, that is propositional logic. Then let us see the definition for proposition, or simply general statement. So simply, a proposition or a statement is, it is a sentence, any sentence, but for this sentence to be a proposition, its truth value must be either true or that of this one, that is false. Generally, a proposition or a statement is a sentence which has a truth value either true or that of false, but not both at the same time. Therefore, any sentence which can satisfy this condition, or whose truth value is either true or this one that's simply false, but not both at the same time, is said to be normally this one, that is a proposition or a statement. If we see some examples for this one, for example, if we consider this thing that simply grass is green, so that the truth value for this example could be either true or that of false, which depends on the greenness of this one, that's simply grass. If grass is green, the truth value for this one is true, but if the color of grass is different from that of this one, that's simply green, it could be the truth value for this statement will become false. Therefore, whatever it is, the truth value of this sentence could be either of these two, that's simply true or false, and it cannot be both true and not false at the same time. So that this is a good example of proposition or statement. If you consider again this one, that simply a triangle has four sides, the truth value for this one cannot be out of these two, that's simply true, or this one, that is false, and it cannot be both true and that of false at the same time. If the number of sides of a triangle is 4, truth value for this one is true. But if the number of sides of a triangle is different from the other 4, so that the truth value for this one could be false. Anyways, these two are good examples of this one, that is a proposition. But if we see a sentence but which are not propositions, for example, if you consider this one, that's simply how old are you? The truth value for this one, or simply how old are you, cannot be either true or that of this one, that's simply false, or this sentence cannot be answered by saying true or that of this one, that's simply false. So that this is a sufficient condition for this sentence not to be a proposition, because the truth value is not neither true nor what, false. Again, if you see this one, that's simply God bless our country, there is also a good example of sentence, but which is not a proposition, because again the truth value of this sentence cannot be either of these two, that's simply true or that of false. So that God bless our country is a sentence, but which is not a proposition, which is not a proposition. So that this is what the definition and the example of a proposition is. Okay, the next one will be, the next thing which we are going to consider will be logical connectives. So that, let us see first this definition. This one, that is logical connectives are, they are words or they can be phrases that are used to connect to or more propositional or predicate logics in such a manner that the resultant logic depends only on the input logics and the meaning of the connective which we are used, or simply which is used. That means the main advantage of logical connectives is, as we clearly state here, they are connectives, or simply they are words or simply phrases which are used to connect any two or more propositional or predicate logics. Therefore, they are applicable just to form compound statement which we are going to consider later. And then in mathematics, we have about 5 logical connectives. And these are the 5 logical connectives which we are going to consider will be. The first one is this one that's simply not, which can be denoted by or symbolized by using that of this one. And the next one is this one that's simply or, which is symbolized by using that of this thing, which is a capital letter B. Next one is conjunction, that conjunction or simply and, which is denoted or represented by using that of this symbol. The next one is because logical connectives can be phrases. The phrase that is if, then, or implies. And lastly, or simply the fifth logical connective said to be if, and, only if, which is symbolized by using that of this thing. Now, if we have these 5 logical connectives, let us see the property and the characteristics of each and every logical connective that are listed here. By the way, the previous one that simply simple proportion, generally proportion can be represented by using that of any small letter alphabet such as P, Q, R, S, and any other or simply any letters can be used just to represent or denote any proposition. So the first logical connective which we are going to consider could be conjunction or simply and. So that the definition for this one would be or when two propositions are joined with the connective, this one that's simply and, then the proposition formed is said to be a logical conjunction. A logical conjunction is a proposition which is obtained by connecting any two simple propositions by using the logical connective that is and or what? This one that is conjunction. And this one that's simply conjunction or simply and is denoted or represented by using that of this thing. And so the logical conjunction or the compound statement which is obtained by connecting two simple propositions by conjunction could be P and Q is written as in this form, that is PQ, P and Q. So that is P and Q, this statement is said to be a logical conjunction. Here, P and Q are said to be the components for the logical conjunction, and we have this one that's simply the logical conjunction that is P and Q, or the truth value of P and Q is said to be true if and only if both the component statements P and that of Q are true at the same time. That means the logical conjunction P and Q is said to be or simply will have a truth value which is true if and only if both P and this one that's simply Q are true at the same time. But if either of these two component statements or both the two component statements are false, so that the truth value for the logical conjunction will become false. So that it will be true only when both P and Q or simply the component statements are true at the same time. So the possible truth values of the logical conjunction within or simply using the truth value, truth table. We have this table that simply the component statements are P and Q. So if these two simple statements are joined or connected by using that of and or conjunction, we'll have this logical conjunction. So the possible truth value for the component statements will be both can be true. The first can be true and second can be false. The first can be false and second can be true, or both P and Q can be false at the same time. And with that, just we have said that this logical conjunction will become true only when both the component statements are true. So that only in the first instance or simply this possibility, this could be true. But in the second case, when P is true and second one is false, true and the false will become false. False and true is also false. Now false and false is also this one that's simply false. If we see some examples for this one, let us consider the following simple proposition, that is A, grass is green, which is true, and B, which is represented by using that of Q. 3 is an even number, which is a false statement. And lastly, it's the simple statement that is R, which is 2 is a prime number, which is true. Then the logical conjunctions, for example, this one that simply P and Q is false. That is, P and Q means what is P? P is grass is green and 3 is an uneven number. So that's because, for example, in the second case that simply Q here, 3 is an even number, is a false statement, even though the first one that simply P is true, that is green, grass is green is also true, so that is true and the false will becomes false. Because for this logical conjunction to be true, both P and Q must be true at the same time. Similarly, if you take this one that simply P and R is true, that means if this logical conjunction is true, that means that P and R, that is both the component statements are true at the same time. What does P says? Grass is green, which is true. What about R? That is 2 is a prime number. We know 2 is prime, so that both are true, so therefore 2 and 2 will become true. The second logical connective is said to be distraction, or and the corresponding word for this one will be, that is or. The definition for this one will be when two propositions are joined by or joined with the connective, this word that simply or, then the proposition formed is called logical distraction. That means logical distraction is simply nothing, but it is a proposition which is formed or simply obtained by connecting any two propositions by using distraction or simply this one that is or. The word distraction or simply or is denoted or represented by using that of this one, which looks like that of capital letter B. So the logical distraction, that is a compound statement which is obtained by obtained by connecting two simple propositions by using that of this one that is or. P and Q is written in the form of this one that is P or Q. And it can be this one that's P or Q can be read as P or Q or P distraction Q. Sometimes we can read this one that's simply P or Q as P distraction Q. When we go to that of their truth values, the truth value of the logical distraction that is simply P or Q is said to be false if and only if both the component statements P and Q are false at the same time. But if either of the two or simply both the component statements are true, then the logical distraction that is P or Q is said to be or simply will have a truth value which is true. Using a truth table, the possible truth values of this logical distraction could be, that means first the possible truth values of this compound statements are both can be true. The first can be true, or simply this we have four possibilities because we have two component statements, so that the truth value of the logical distraction will be true because in this case both P and Q are true. This is also true because the first one is true, even though the second component that is simply Q is false. And because the logical distraction that is P or Q is false, only when both P and Q are false at the same time, that's simply here. Except this one, with the other possibilities, the logical distraction will have a truth value which is true. If we consider some example for this one, taking the component statements to be which we are considering in the case of that of logical conjunction. Let P be a simple statement that is grass is green, which is true. Q, that is 3 is an even number, which is false. And the logical distractions could be, that is P or Q. P or Q means that simply this one. P or Q means that is grass is green, or 3 is an even number or simply even number. Because the first component that's simply Q, P here is true, even though the second component Q is false, so that true or false is true. Because for this logical distraction to be false, both P and Q must be false. Okay, the next one, or simply the third logical connective which we are going to consider will be this one, that is implication or if then. The definition could be when two propositions are joined with the connective that is implies or if then the proposition format is called a logical implication. This one that is implies is denoted by using that of this arrow. There is a representation for if then or simply implies. So the logical implication of the proposition P and Q is written in the form of this one, that simply P implies Q, which can be read as P implies Q, or if P then Q. Sometimes we can read this one as Q if P, Q if P. So that these are the possible way of reading this one, that simply P implies Q. And when we go to that of the possible truth value of the logical implication, that is P implies Q, we know that P implies Q is false only when the first statement that simply P is true and second component of the conclusion that is Q is false. But except this possibility, the truth value of this logical implication will become true. That means the only possibility for this statement or logical implication to be false is that the first, or simply the if statement, must be true, and the conclusion that is second statement, which is Q, must be false. Except this one, the logical implication will have a truth value which is true. Using this a truth table for this one, we have logical implication here with components P and Q on this one. So we know that this one, that simply P implies Q, will become false only when P is true and Q is false. So that in this case, the possibility is only this one. That means only this option will produce a logical implication with a false truth value. Except this one, have the truth value of this logical implication would be true. That means true implies true is true. False implies true is also not true. False implies false is even. And this one, that's simply true. An example for this connective will be, again, let us consider these three simple statements, which are P, that is grass is green, 3 is an even number, 3 is a prime number. Then the logical implications. The following logical implications, for example, that simply P implies Q is false. That means when we say that P implies Q is false, it means that the if statement, or simply the first statement, P is true, and the conclusion that is Q is false. Because what is P here? P is grass is green, which is true, but Q, 3 is an even number, so that the is false. So therefore, true implies false will be this one, that's simply false. Next one, that simply if you consider Q implies R is true. That means in this case, if Q implies R is true, automatically we can conclude, or we can be sure that the conclusion that simply this one, that is R must be true. R, that means there is a possibility for this one to be that of true. But if this is false, the if statement that is Q must also be false at the same time. But whatever this one, or simply the truth value of this one, that simply Q is, if R is true, then automatically Q implies R will becomes a true statement, or simply component statement, or a logical implication will have a truth value which is true. Therefore, when we see the truth values of Q and R here, what is Q? That is Q3 is an even number, which is false. And this one, that simply R here, R is a prime number, which is true. So that false implies true will becomes true. Okay, the fourth logical connective will be by implication. The case of by implication, when two propositions, that is simple propositions, are joined by this one, that is a connective which is by implication, then the proposition formula is said to be logical by implication. or are logical equivalent. The other name for logical implication is said to be logical equivalence. A by implication, or simply if and only if, that means, is denoted by using that of this symbol, and the logical and by implication of two proposition P and Q is written in the form of this one, that's simply P if and only if Q, which can be read as P if and only if Q. And when we come to that of the truth value, the possible truth value of this logical by implication, P if and only if Q is false, if and only if P and Q have different truth values. That means if the truth value between P and that of Q is different, that is either P is true and Q is false, or vice versa, so this logical by implication will have a truth value which is false. But if the truth value P and Q are similar, that means if both are true or both are false at the same time, the logical by implication will have a truth value which is true. Then the possible truth values of this logical by implication within that of a truth table. Sorry, there is no truth table for this one, for the disturbance. So let's proceed to the last one, or simply the last logical connective, which is negation or not. Here, actually, we are not able to, or simply we may not consider this one, that's negation, to be logical connective, because it is applicable only on a single proposition. It doesn't have a power to connect two propositions together. So given any proposition P, then we can form a proposition which is this one, that's the negation of P, which is called the negation of P. Then the truth value of negation of P, which is the opposite of this one, or the negative of this one, that negation of P is false, if the original statement that is P is true, or the negation of P will be true if and only if the original statement that is P is false. Then using a truth table, the truth value of this one, the possible truth value of this negation of P will be, when P is true, its negation will be false. When P is false, the negation of this one, that's negation of false, will be this one, that's simply true. The examples could be, let us consider again these three simple statements, so that the negation of the upper propositions will be, for example, the first one, that's negation of P will be, because his grass is green, so that its negation will be, grass is not green. Here it was true, but its negation will becomes false. Second one, that's simply Q3 is an even number, so that the negation of this could be negation of Q, which is 3 is not an even number. Here Q was false, but its negation, that is negation of Q, which is 3 is not an even number, will becomes proposition with, which is true. And lastly, the negation of the statement that is R, which is a prime number, could be negation of R, that is not a prime number. Here is a prime number was true, but it is negation, that's negation of R, that will becomes a false. Okay, this is about logical connectives. So let us see the application of logical connectives in forming compound or complex propositions. So let us see first the definition of compound statement or compound propositions. The definition will be the propositions formed by joining any two or more propositions by one or more logical connective or connectives is said to be a compound statement or a compound proposition. As an example, if we consider P given that of R to be that of simple propositions, so if we connect these three simple statements by using that of two logical connective, which is implies in that of conjunction, so that we can obtain this statement, which is said to be a logical, a compound proposition or complex proposition. Even if you consider this logical disjunction P or R, there is also another example of compound statement. P if and only if Q implies R is also a good example of that of compound proposition. Then, with regard to that of the evaluating the truth value of the compound statement, we have this remark or simple notation or this thing. Whenever this one that simple disjunction or conjunction is occurring or simply comes in combination with if then and this one that simply if and or if, so we shall assume or simply we must give a priority for this one that's simply disjunction or conjunction, and then we have to solve or simply next application will be for this one that's simply then or this one that is if and only if. As an example, for this one, for example, if we have a statement or simply a compound statement of this form, that is P or R implies P and Q implies this one that is R. This means because this one that is conjunction is combined with this one that simply implication or simply implies, so that we must solve or simply have a truth value for the first one or simply first for the logical conjunction. Therefore, we have to take this one that simply P and Q, then implies this one that is R. Using this remark, that means. Similarly, if we have this thing, for example, here, we know that again here, the logical disjunction, that is or, is combined with if and only if. So that we must give a priority first for logical disjunction. Therefore, the logical is identical with this must be enclosed by a bracket. That is, priority must be given for this one first. So that next we have to give or simply apply for the logical by implication or simply if and only if. Similarly, if both are negations, so we have to determine first the truth values of negations separately, and we have to combine by or simply apply the property of the logical connective, which is used to connect them. Again, that is for we are using to logical connective, which is implies and if and only if, so that because there is no distraction or conjunction here, we must give a priority for the first logical connective, that is if, and therefore the equivalent or simply this means the negation of Q implies negation of P if and only if R. That means we must give priority for the first logical connective or simply the two propositions which are connected by using that of the first logical connective, and next for the next one. Okay, we have this definition on compound proposition again. The definition says two compound statements P and Q are said to be equivalent. That means the definition is on equivalent compound statements. These two compound statements are said to be equivalent if and only if they have the same truth value for all possible combinations of truth values for the component propositions occurring in both the compound statements P and Q. That means these two compound statements will become equivalent if and only if the two compound statements are having the same truth value for every assignment of their truth values for simple components that are involved within the compound statement themselves P and Q. But if there exists at least one possibility for this two compound statements to have different truth values when for the same assignment of their truth values for their compound statements, then that will be a sufficient condition for these two open propositions not to be equivalent to each other. But if they have the same truth value, then they are equivalent, and now we can write in this form that there is an equivalency. As an example here, if we consider an example for this one, let us consider these two compound statements that simply in the Q, where P is P implies Q and Q is negation of P or Q. So let us see whether these two statements are equivalent to each other or not. Similarly, let us consider this one that is simply R, P and Q if and only P, and another statement that's simply S, which is P implies Q. So the first one that is simply here, using a truth table, here the first component statement is P implies Q. Second one is negation of P or Q, so that the component statement for this one are P, Q, and the negation of this one, that's negation of P. The possibility this one, that's simply the possibility for the truth values of these two component statements are, this thing that simply we have 4, so that the truth value for this first component or simply compound statement, which is P implies Q, will be this one. That means true implies true is true, true implies false is false, but the rest are true. Therefore, here we do have the possible truth value of the first compound statement, that is this is for P. Similarly, Q, that is negation of P or Q, which is logical destruction, the truth value will be again this one. This is the compound statement, which is Q. So when we compare and contrast the truth values of these two compound statements, that is the last two columns of this table, so they do have the same truth value. That means for the first case, both are true, both are false here, true, 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 true. Therefore, because the truth values of these two compound statements are identical or simply the same for the same assignment of the truth values for the component statements, so that these two compound statements are said to be equivalent to each other. So we have this conclusion, that is P and Q are equivalent, or P equivalent to Q. The second example, or simply the solution for the second example, will be this one. That is the first compound statement is P and Q, if and only if P, and second compound statement that is S, which is P implies Q. The possibility for the truth values of the component statement is the same, which is because we have only two component statements P and Q, so that we have 4 possibilities. Therefore, first let us see P implies Q here. The truth value for P implies Q with this one, and in order to have a truth value for this one, we have to first find P and Q here, so that true and true is true, but the rest are false here. Therefore, if we combine that, in order to determine the truth value of this one, we have to consider the elements that is P and Q, that is simply this one, and Q, which is the first element of this table. And these two elements are joined by using that of logical by implication, or simply by if and only if. Therefore, remember that when two simple statements are joined by using that of this one, so that the logical by implication will be true if and only if both the component statements have the same truth value. Therefore, in this case, for example, in the first case, here P is true, and P and Q is also true, so that true if and only if true is true. Similar second one, P is true here, but this one, that's P and Q, is false, so that true if and only if false is false, the rest are true. Therefore, if we see the element that's simply this, and the last element of this table, that's simply this one, if you observe that their truth values, they have the same truth values, or simply their truth values are identical. That means here it is true, this is also true. It is false, this is also false. This is true, this is also true. True, true. Therefore, depending on the definition that already we have seen previously, for the equivalency of two compound statements or propositions, these two compound propositions are equivalent to each other. That R is equivalent to S. The next thing which we are going to consider will be about converse, inverse, and contrapositive of a logical implication, which is this were applicable on a special type of compound proposition, which is logical implication, which is a compound statement which is obtained by using that of if then or simply implies. So the definition could be, let's assume that we have this logical implication, which is P implies Q. Then the converse, inverse, and contrapositive of this logical implication will be the first case, this Q implies P said to be the converse of P implies Q. That means this statement is obtained from this one by only interchanging the if and the conclusion of the logical implication. In this case, in the case of that of the converse of the logical implication, the if statement of the converse could be the if statement, the conclusion of the original logical implication, and the conclusion of the converse could be the if statement for the original logical implication. So that a statement which is obtained by interchanging the if and the conclusion of a logical implication is said to be the converse of the logical implication. And that means here's the explanation for this one. That is, the hypothesis of the converse statement is the conclusion of the conditional statement, and the conclusion of the converse statement is said to be, or it becomes the hypothesis of the conditional statement. The conditional statement. The next one is inverse of a given statement or logical implication. The inverse of a logical implication will be obtained from the logical implication itself by only taking or simply making both the hypothesis or simply the if and the conclusion of the logical implication to be their negatives, or by negating both the if and the conclusion of the conditional statement, so that negation of P implies negation of Q is said to be the inverse of this logical implication. And lastly, the contrapositive of this thing, that is this logical implication, would be the negation of Q implies negation of P. Negation of Q implies negation of P. That means the if statement, or simply the hypothesis of the contrapositive of the given statement, could be the opposite or the negative of that of the logical implication, the negative of the conclusion of the logical implication, and the conclusion of the contrapositive of a logical implication could be the negative of the hypothesis, or simply the if statement of the original logical implication. Therefore, a statement which is obtained by interchanging and at the same time taking the negative of both the hypothesis and the conclusion of the statement is said to be the contrapositive of the logical implication. One thing that we can clearly observe from this one is that if we compare and contrast the inverse and the contrapositive of the same logical implication, we know that because the contrapositive of the this logical implication is obtained from the inverse or simply from the statement by only interchanging the position of the hypothesis and the conclusion, so that the contrapositive of the logical implication could be the converse of the inverse of the same logical implication. That is, this is the inverse for negation of P implies. The converse for the negation of P implies negation of Q. Therefore, the relationship that is in between inverse and contrapositive of a logical implication. If we see this property by considering some examples, let us consider, for example, this compound statement, that is, if the weather is cold, then the lake is frozen. This is a logical implication. Then what we are asked here is, after we are given this compound statement, we are asked just to determine the converse, inverse, and contrapositive of the same logical implication. First, let us see the converse. In order to determine both the converse and everything here, let us separate the if statement or the hypothesis of this logical implication, and it is conclusion. Let, for example, PB, that is the if statement, or simply the hypothesis of this logical implication, which is the weather is cold, and its conclusion will be can be represented by Q, which is the lake is frozen. Therefore, the logical implication that P implies Q will be, this is the symbolic form of this logical implication, so that if the weather is cold, then the lake is frozen. Therefore, easily we can obtain the converse, inverse, and contrapositive of this statement from this one. The first case, that is the converse of this statement, could be, because we know that the converse of a statement is obtained by interchanging only the conclusion and the hypothesis of the original logical implication. So when we interchange Q and P, we have Q implies P, or if Q, then P, or P if Q, so that if the lake is frozen, then the weather is cold. So that this could be the converse of this statement, which is if the weather is cold, then the lake is frozen. And the inverse of this thing will be, we know that the inverse of the statement, or simply this logical implication, will be without changing the conclusion and the hypothesis of the statement, we only negate or simply take the opposite or the negative of both the if statement and the conclusion. So that in this case, negation of P implies negation of Q will be if the weather is not cold, then the lake is not frozen. If the weather is not cold, then the lake is not frozen could be the inverse of this statement, which is if the weather is cold, then the lake is frozen. And lastly, the contrapositive of this statement could be this one. That means the contrapositive of this thing, or the converse of the inverse of the statement that simply this one would be, that's negation of Q implies negation of P. If the lake is not frozen, then the weather is not cold. If the lake is not frozen, then the weather is not cold. It could be the contrapositive of this statement, which is implies Q. Okay, the next one is, again, we are on compound statements. There is tautology and contradiction. So let us see first their definitions. The first definition for tautology would be, tautology is a compound statement, first case, which is always true regardless of the truth values of its compound propositions or statements. So that whatever the component, the truth values of the compound statements are, if the truth value of the compound statement is always true, then the type of compound statement is there to be a tautology. Whereas the contradiction could be, again, it is a compound statement or a compound proposition which is always false regardless of the truth values of its component proposition. So that whatever the truth values of its compound statements are, if the compound statement has a truth value which is always false, then that type of compound statement is said to be a contradiction. But there is another group of compound statement which is in between these two, that is tautology and contradiction. That means the truth value of a compound statement could be true for some instances and can be false for the other instance or simple possibilities. So that there is a compound statement which is neither tautology nor contradiction, so that such type of compound statement is said to be contingency. So that contingency by itself is a compound statement like tautology and contradiction, but a compound statement to be contingency, the compound statement must be neither tautology nor contradiction. If we see this by considering some examples, and first, that is, the example states that determine whether the following statements are tautology, contradiction, or contingency. So let us consider these three examples. If we see the first one, in order to see the possible truth value of the given compound statements, using a truth table will be very important. So that for the first one using this table, we have the compound statement that is simply P implies P or Q, that is simply this one. And therefore, from the truth table, which is already prepared here, we know that the truth value of this compound statement is always true, or simply every truth value here is true. Whatever the truth values of this compound statement, that is P and Q, and P or Q are. Therefore, the statement that simply compound statement P implies P or Q is said to be a good example of that of tautology. P implies P or Q is a tautology because the truth value of this one of the compound statement is always true. Next, the next one that simply B, the given compound statement is this one that simply P and P implies Q implies Q. So that means this one. Therefore, again, applying or simply using the idea or simply the advantage of this one that is not truth stable, we have the component statement is P and Q. We have P implies Q here, and P implies Q. So if we connect these two by again, this one with respect to that of Q by, and this one if then, we have this truth value. So that in this case, as we clearly observe here, because the truth value of this compound statement is always true, whatever the truth values of the component statement is given this table, so that this compound statement is a tautology, very like that of the first one. Therefore, P and implies Q, implies Q is a tautology. And lastly, the last solution for the last example could be that is P and negation of Q and P and Q. The component statements are again true, so that the possibility for the truth values of this one is 4. So when we see here, the last column of this table again, that means we know that the truth value of this compound statement is always false. There is no any true truth value. Therefore, a compound statement which is always false, whatever the truth values of its component statements are, is a compound statement which is a contradiction. Therefore, P and Q and P and Q is a good example of that of contradiction. Therefore, there is what about contradiction and tautologies. So the next one could be this one that is open proposition and contradiction. So let us see first what open propositions are. Therefore, the definition would be an open statement, or also called a predicate, is a sentence that contains one or more variables and whose truth value depends on the value assigned for the variables. Generally, an open statement is simply a statement which involves one or more variables, but which can be converted into a proposition if we assign the variable or simply the variables by a certain value. Totally, the truth value of the open statement is on the type of value, simply the value that can replace the given variable. And notationally, open statements can be represented by capital letters followed by the variable or simply the variables that are involved within the open proposition, like P of X, Q of X, R of X, Y, if it involves two variables. As an example for this one, here we have X is a month before September. There is an open proposition because of the involvement of the variable that is X. So that the truth value of this one, that simply this open proposition, will depend on a month that can replace the variable which is X. If the month that can replace this one that is X is a month just before this one, that's simply September, this could be true. But if the months that can replace this one that simply exists, which is not after or simply before or simply after this one that simply September, so that the truth value of this open proposition will becomes false. Next one is x plus 4 is equal to 100. This is again another good example of open proposition. So that the truth value of this open statement or simple proposition is again depends totally on the value of the variable or simply the value that can replace the variable which is x. So that if the value that can replace x is exactly a value which can be added with 4 and gives this one that's simply 100, so that the truth value for the open statement will be true. But if we replace by a certain number for x, and if it is added with 4 and gives different from that of this one, that's simply 100, so that the truth value for this open proposition will be false. And last example for this one could be why is it in Ethiopia? So that the possible value for this one is the set of cities. Therefore, if the city that can replace this one that simplifies ST in Ethiopia, it becomes true. But if it is out of Ethiopia, it becomes false. Therefore, anyways, these are examples of open propositions. Then, as we have this remark or simply note, the collection of all allowable values for the variable in an open sentence is called the universal set or the universe of this denoted by using that of capital letter U. For example, if you take, for example, that simply this one, that is x plus r 4 is equal to 100. The possible values of this one are simply x, if it is not clearly specified here. So this could be a set of real number. Therefore, set of real number will be the set containing the collection of all allowed values of the variable that is x. So that set of real number could be taken as a universal set for this open proposition. And the notation for the universal set will be capital letter U. Again, let's have this definition. Again, on equivalency of open proposition. Two open propositions P of x and this one that Q of x are said to be equivalent if and only if P of A is equal to Q of A for all individuals of this one that is A. That means we have these two open propositions for P of x and Q of x with their corresponding universal set that's simply U, so that if P of A and Q of A have the same truth values or simply identical, for every A within the universal set there, then the two statements P of x and Q of x are said to be equivalent to each other. That means this one. If the universe U is specified, then P of x and Q of x are equivalent if and only if P of A is equal to Q of A for all A an element of this one that is A. But if there exists at least one A within the universal set that's simply U, which can make P of A and Q of A to be that of difference, so that will be a sufficient condition for these two open propositions not to be equivalent to each other. Not to be equivalent to each other. As an example here, let the first open proposition be P of x with x squared minus 1 is equal to 0. The second one, that's Q of x, is the absolute value of x greater than or equal to 1. And let's consider simply, let's assume that the universal set will be set containing these four elements, which are minus 1 over 2, 0, and 1. Then, if we are asking just to determine whether P of x and Q of x are equivalent or not, we have P of x, Q of x, and the universal set here. Then, what we need to check or simply show here is that P of A is equal to Q of A for all an element of this set, for all an element of this set. So let us substitute each and every element of this one that is U in P of x and Q of x, and let us see whether P of x and Q of x are the same for every an element of this set that's simply U. The first case, for example, that's simply P of minus 1 is true, because if you substitute minus 1 here, minus 1 square is 1, 1 minus 1 is 0, so that 0 is equal to 0. That is why this is true. Similarly, what about Q of 1? You substitute, minus 1. You substitute minus 1 here. The absolute value of minus 1 is positive 1, which is greater than or equal to 1. Again, it is true. So that P of x and Q of A are the same or simply identical for is equal to minus 1. Similarly, for the second element of the universal set U, P of minus 1 over 2 is false, because if we substitute minus 1 over 2 for x here, we have minus 1 over 2 square, which is minus 1 over 4. Minus 1 can never be 0, so that this is different from that of 0, so that is why this is false. Similarly, Q of negative 1 over 2 means the absolute value of minus 1 over 2 is positive 1 over 2, but positive 1 over 2 can never be greater than or equal to 1, so that this is also false. Therefore, both Q of negative 1 over 2 and Q of negative 1 over 2 are the same here. Similarly, if you take the third element of the universal set, that's 0, Q of 0 is false, Q of 0 is also false, so that they are identical. And lastly, if you take 1, Q of 1 is true, Q of 1 is also true. Therefore, as we clearly observe here, the two statements P of x and Q of x have the same truth values, or simply they are identical for every A, which is an element of this set that's simply universal set, because P of minus 1, 0, true. At negative 1 over 2, both are false. At A is equal to 0, both are false again. And at A is equal to this one, that's simply 1, both are true. Therefore, from here, P of A and Q of A are identical for all A and element of U, so that they are equivalent to each other. Okay, let us see the next definition again. Let's assume that we have a universal set that simply set U, so that an open proposition P of x is said to be tautology if and only if P of A is always true for all values of A, which is an element of the universal set that's U. That means we can define, or simply we can have an open proposition which is either tautology, contradiction, or contingency, so that an open proposition P of x is said to be a tautology if and only if this one that's simply P of A is always true for all values of A within the universal set that's simply here. Similarly, an open proposition P of x is said to be contradiction if and only if P of A is always false for all values of A, which is an element of U. So that if for every A an element of the universal set, if the open statement is always false, so that open statement is said to be contradiction. Whereas if the open statement, or simply P of A is always true for every values of A, which is an element of the universal set, then that type of open statement is said to be this one, which is a tautology. As an example, let us assume that the universal set be a set of real number, and the first open proposition will be P of x, which is equal to x squared greater than or equal to 0. And second one, that's Q of x, which is x squared less than 0. So that in this case, for example, that's simply here. For P of x, x squared greater than or equal to that of 0 is here to be, or simply for any real number, that is, if you substitute any real number for x here, we know that the square of any real number is greater than or equal to that of 0, so that really this statement is a tautology. But if you take this one, that is Q of x, which is Q of x, x squared less than that of 0, we know that the square of any real number can never be less than that of 0, so that this statement is always false for every real number, so that this is a contradiction. Okay, the last session for this one, or simply this video, will be about quantifiers. First, let us see what quantifiers or simply proportions are. Given an open proposition P of x with a universal set that simply set U, then we have the following three possibilities. What are the possibilities here? That means if we are given any proposition P of x, and it is universal set that simply set U, so that depending on the property of the truth values of this open proposition will be a tautology, that is, it can be true for all x an element of this one, that's universal set U, or it can be true for some x which is an element of U and false for the others, or the open statement that is P of x can be always false or simply false for all x an element of U. In this case, that is, if P of x is true for all x an element of U, becomes a tautology. The second case, if P of x is true for some x and false for the others, it becomes contingency. Where in this case, if P of x is false for all x an element of U, so that this could be a contradiction. Then, depending on this one or simply this possibility, the first quantifier which we are going to consider will be universal quantifier. By the way, we have two types of quantifiers, which are universal quantifier and existential quantifier. The universal quantifier could be represented by using this one, which looks like that of an inverted capital letter A. So that's the phrase for this one, or simply universal quantifier, would be for every x, or there are also other phrases that can characterize this one. That is, with regard to simplify this quantifier for every x, for all x, or for each x. All these three have the same meaning. So that's the symbolized form of this one could be this one, or simply universal. This is the universal quantifier, and this one is x. So that for every x. Therefore, this could be this symbol could be read as for every x, or for each x, or for all x, for all x. Okay, the second type of quantifier is existential quantifier, which is symbolized by using that of this one, which looks like that of an inverted capital letter E. So that the phrase for this one, or simply existential quantifier, would be there exists an x. Correspondingly, we have also another phrase, there exists an x, or for some x, or this one, or simply for at least one x. And additionally, it could be symbolized by using this one, that simply there exists x, or for at least one x, or for some x. Be a meaning for this one. And all these have the same meaning. If we see these remarks, we know that in order to show that the open statement, or the quantified open proposition, which is quantified by using that of universal quantifier, which is for every x P of x is false, it is sufficient to find at least one element that's simply A within the universal set, such that P of A is false. And the element here that is A is said to be counter example, that is disproving using that of counter by using a counter example. But if we are not able to find at least one A that can make this one that's simply P of A to be that of false, so that the quantified proposition for every becomes true. But if we can find at least one x, or simply one A within the universal set that can make P of A to be that of false, then that will be a sufficient or simply necessary condition for every x P of x to be false. Similarly, a quantified proposition which is quantified by using that of existential quantifier, that is, there exists an x, or there exists at least one x, or for some x, P of x is false, if we cannot find any A which is an element of U having the property of P, or there exists an x, or simply this quantified proposition will become true if we can find at least one a, which is an element of u that can satisfy the property of this function. So that we can find at least one a that can make this one to be that of true, so that there exists at least one x satisfying the condition of p of x will be true. But if we are not able to find any a within the universal set having the property of this one, that's simply p of x, so that this quantified proposition will be false. Okay, let us consider examples. They consider the following open propositions. That is, the first open proposition which we are going to consider could be p of x, which is equal to x squared minus 2x less than 0. And second one is k of x, which is x minus 1, the whole square greater than 0. Then we are asked just to determine the truth value of the first one is for some x, that is for some real number x, or for at least one real number x, x squared minus 2x is less than 0. So the truth value of this one could be true if we can find at least one real number x that can satisfy the property of this inequality. So as an example, if you consider one, a real number 1, that is, if we substitute x by 1, 1 squared is 1, minus 2 times 1 is, that is simply 1 minus 2, which is minus 1. Minus 1 is less than 0. So that due to only the existence of this real number, that's simply 1, which can satisfy this condition, so that the truth value for this one could be that is true. Similarly, the next one, that's simply this one, for all x, or for every x, or for each real number x, the condition that is x minus 1, the whole square is greater than 0. In order to determine, or simply we know that from the definition of that of universal quantifier, we know that the the quantified proposition, which is quantified by using that of universal quantifier, is false if and only if there exists at least one element that is simply x within the universal set, in this case a set of real number, that can make this property to be false. For example, in this case, if you take x is equal to 1 again, x is equal to 1, which is a real number, and if we substitute 1 here, we have 1 minus 1, which is 0, 0 square is 0, but 0 can never be larger than that of 0. So that in this case, due to the existence of this only this element, even though we can find others, so that the truth value for this one could be false. That is false. As an example, we can consider x is equal to this one, that is 1. The same thing for the first one. That means there exists x an element of R, x squared minus 2x less than 0. You know that if you substitute 1 here, that it is false, so that the first one is true. Hence, there exists an element of R x squared minus 2x less than 0 is true. For the second one, for every x an element of R, x minus 1 squared greater than 0, you substitute again 1, there is false, so that for every x, or for each x, or for all x, for all real number x, x minus 1 the whole square greater than 0 is false. The next one is the relationship that exists in between quantifiers, because we have two quantifiers which are universal in existential quantifier. What is the relationship that exists in between these two pair of quantifiers? So that in order to see the relationship that exists in between these two quantifiers, let's assume that, or simply let's have p of x be any open proposition. Then we know that from the definition that already we have seen previously, for this quantified proposition p of x for every x, or simply for all x p of x to be false, only if we can find an individual a in the universal set, that is because we must have a universal set here U such that P of A is false. Or this quantified proposition for a break P of X is false if and only if we can find an individual or simple element A in the universal set that can make the negation of P of X to be true. Or generally from its general definition, this could be false if and only if there exists at least one element within the universal set that can make the open statement P of X to be false. That means if we succeed in getting such an individual, then the existence negation of P of X could be true. That means if this A can make P of X to be false, for every X P of X will be false. If this A can make P of X to be that of false, the same A should make the negation of P of X to be true. Hence, for every X P of X will be false only if there exists an X or simply for some X, negation of P of X is true. So, in this case, for every X P of X is, or simply the negation or simply the opposite of this one for every X P of X is, the for some X negation of P of X. Because for this to be that of true, this must be false. I mean, for the first one, that's simply this one to be that of false, this is true. If this is false, this must be true. That means that these two are opposites, or simply they are, one is the negative of the other. Similarly, the negation of this one, or simply the negation of for some X, or for at least one X P of X is, or every X, the negation of K of X. So we have the following conclusion, or simply summations. Here, the negation of for every X P of X is equivalent to for some X negation of P of X. That means in order to find the negation of this one, the negation of universal quantifier will be replaced by using that of existential quantifier, and we have to take the opposite, or simply the negation of the open statement. Similarly, the negation of the for some X P of X could be like that of the first one. The opposite, or simply the negation of existential quantifier, will be replaced by universal quantifier. Here it is P of X, so that the negation of this one will be followed. Therefore, there is what the relationship that exists in between these two quantifiers. We can see this one by considering an example. Let's have U to be the set of real numbers, that's the universal sets. Then the negation of for some X squared minus X less than 0 is equivalent to, depending on this definition that already we have seen here, the negation of existential quantifier is universal, and this is P of X, so that this negation will be the negation of X squared minus X less than 0. But what is the negation of X squared minus X less than 0? Its negation would be, for every X here, there is for every X, the negation could be X squared minus X, here it was less than, it should be greater than or equal to that of 0. Therefore, these two, that is the negation of this thing, and these two are equivalent to each other. That means they must have the same truth value. Similarly, if you consider another thing that's simply this one, for every X, that's the negation of for every X plus 1 is equal to 0 is equivalent to, if you distribute this negation here, the negation of universal is existential, and the negation of X plus 1 is equal to 0 will be this one, that is X plus 1, different from that of 0. Therefore, the negation of for every X plus 1 is equal to 0, and for some X plus 1 different from 0 are equivalent to each other, because the second one, this one is exactly the negation of this thing. Okay, the next thing which we are going to consider could be compound propositions containing quantifiers, like that of compound proposition, which are formed by connecting simple propositions. We can also have a special type of compound proposition, which are containing or involving quantifiers. So let us see this remark or simple enough first. If we have proposition containing quantifiers, we can form compound quantified proposition by connecting them by any logical connecting. If we have a number of compound propositions involving quantifiers, that we can connect them by any logical connective that we have in order to form a compound statement which contains quantifiers. If we see an example for this one, that is compound statement containing or involving quantifiers, let the universal set be the set of integers. And the first open proposition be P of x say that x is a prime number, and second one is Q of x, that is x is an even number, and lastly R of x, that is x is an odd number. Then the truth value of this one, or simply for some x, or for at least one x, P of x implies Q of x is true. Know that for this statement to be true, because it is a quantified proposition which is quantified by existential quantifier, it is enough just to obtain an integer, or simply at least one integer, that can make P of x implies Q of x to be true. Know that for this one to be that of true, either or simply this will be false only when P of x is true and Q of x is false. But because of this one, or simply existential, by using that of an example, or simply if we can find at least one integer which can make this logical implication to be true, so that totally this quantified proposition will become true. So, for example, if we take x to be an integer that's simply x equal to 2, if we consider x equal to 2, we know that what is P of 2? P of 2 means 2 is a prime number. Exactly, this is true. This is true. That is true at 2, where at x is equal to 2. And what about Q of 2? Q of 2 means 2 is an even number. It is also even, so that both P of 2 and Q of 2 are true. So that 2 implies 3 is true. Therefore, this is true. If you take a counter example here, you can consider x is equal to this one, that is 2. Even we can also we may find another integer that can make this statement to be true. Since it is existential, it's enough just if we can obtain at least one. Second one, that is for every x. For every x, P of x implies Q of x is. This is a false statement. We know that because this is the universal quantifier. For this quantified proposition, which is quantified by using that universal quantifier to be false, it is sufficient, or simply to obtain at least one integer which can make P of x implies Q of x to be false. So again, if we take, or simply if we consider again the previous example, that's simply 2 again here, what is P of x? P of 2. P of 2, that is x is prime number, is true. This one is true at x equal to 2. But what about Q of 2? Q of 2, that is x is an even number, and that is Q of x. X is an even number. This is also true, that is true implies true. That could be true. But what about if we take another thing? For example, that is, if we take, for example, that is simply 3. And that is, if we take x is equal to this one, that is simply 3, we know that P of 3, that is 3 is a prime number, is true. But Q of 3, that is 3 is an even number, is false. Therefore, at x equal to 3, this is true, but this one is false. So that 3 implies false will becomes false. Therefore, as a counter example, we can consider this one, that is x is equal to 3. And the next one, that's simply C. for every x, r of x or p of x, this is false. We know that this is a logical destruction. For this to be that of false, both r of x and p of x must be false. But in order to logically or simply totally this quantified proposition to be false, it will be sufficient or simply the only necessary condition for this to be that of false is that we need to find at least one integer within this universal set that can make r of x or p of x to be false. That means both r of x and p of x to be false. So we need to have a counterexample again here. So as a counterexample, if you consider what is r of x, the property of r of x here. R of x is an odd number, so we need to find a number which is not odd. That means, what about p of x? P of x is x is a prime number. We need to find an odd that is a number which is a natural, an integer which is not a prime number. So what will happen if we take, for example, that is x is equal to this number that is 4. What is r of 4? R of 4 means x is an odd number. 4 is not an odd number. So in this case, this is false. This is false as x is equal to 4. What about p of 4? P of 4 here, 4 is a prime number, but 4 is not prime, so that this is also false. Therefore, false or false becomes false. Therefore, for every x, r of x or p of x is a false statement. We can consider this one as a counter example, that is x is equal to 4. Okay, so that this is what the truth value of these statements are. The last one for this example could be D, that is for every x, r of x and p of x implies q of x. Again, this is a false because if this one is false because it is universal quantifier, we need to find a counter example like that of this one, that's simply C and B. But what does this make to be false? Let us see the property of the open statements first. What is the property of this one? Because this is a logical conjunction, we know that this compound statement logically will become false only when the first one, that's the logical conjunction, is true, and this one, that is q of x, is false. So we need to find an integer within this universal set that can make the the logical conjunction, that's simply this statement, this compound statement, to be true, and the open statement, that is q of x, to be false. But the property of r of x is an odd number, because we know that this is true only when both r of x and p of x to be that of true. So we need to find an integer which is an odd number first. What about p of x? Again, which is prime number, odd plus prime. So an integer which is both prime and that of odd could be, for example, if we take a number which is both prime and odd, that is, let us consider x is equal to this one, that is 3. 3 is a prime number because it has only 2 factors, and it is also an odd number because it is not a multiple of 2. Therefore, r of 3 and p of 3 is true. But what about q of 3? Q of 3 means this one, that is q of 3, that 3 is an even number. It is not even. Therefore, this one, that simply this is false. This is false, so that this logical implication is true, but this one is false, so that 3 implies false is false. Therefore, as a counter example, this one at x equals 3, for every x, r of x and p of x implies q of x is a false statement. Okay, the last session for this video will be again on quantifiers, which is quantifiers occurring in combinations. Let's have an open statement involving two variables x and y. Then we have the following combinations. The first one is for every x, that is for all x and for all y, P of xy is satisfied. The next one is for some x and for some y, P of xy is satisfied. Or C, for every x, there exists some y satisfying P of xy. And lastly, for at least one x, or there exists an x, for every y, P of x is satisfied. So depending on this possibility, if we consider or see the property of the truth value of this possibility using data for simply considering an example, let's assume that we have the universal set be the set of real number n, the open statement P of x, y, b, x minus y is equal to 5. Then the truth value of the following could be for every x and for every y, P of x, y is true. Or P of x, y will be satisfied means it means that for this quantified proposition to be that of true, whatever you take any value from the universal set or simply in this case set of real number, always P of x, y must be true. Or this one that for every x and for every y will become false only when if we can obtain two real numbers x and y that cannot satisfy P of x, y, or that can make P of x, y to be false. Because we have a number of real numbers that can make this one to be that of false, so that clearly this is false. The next one is for every x, there exists a corresponding y satisfying the condition of P of x, y. Clearly this is a true statement. That means here this one is a false statement. If, as an example, you can take x is equal to y is equal to, for example, that's simply 1. 1 minus 1 is 0, which is different from that of 5, so that this is false. But for this one, for every x, there exists y satisfying P of x, y means this is a true statement because for each and every x, there exists a corresponding y satisfying this condition because we have x minus y is equal to this one that's simply 5. So that whatever you take any value y, any value for the first variable that is x, we can find the corresponding value of y in the form of this one that's simply y, which is equal to x minus this one that is 5. So that this should be corresponding value satisfying this condition, therefore this is a true statement. The next one that's simply C, there exists a fixed x which holds true for every y in satisfying the condition of P of x, y. Here there is a big difference between B and D. Here for each and every real number x, we can find the corresponding y satisfying this condition, which is true. But in the case of this one, there exists a fixed x which holds true for every real number y in satisfying this condition. But there is no any fixed, we are not able to find any fixed real number that is simply x which holds true for every y in satisfying the condition of this open statement that's P of x, y. So that in this case, this is false because if we take, for example, x equal to 1, we can find the corresponding y for this one that is y. But unless x is changing, so that if x is fixed, there is no any other y different from that of that one that can satisfy this condition, so that we are not able to find a fixed x which holds true for every real number y in satisfying the condition of that this is false. And lastly, there exists there are some y's and some x's that satisfying this condition could be really this is a true statement because we have, or simply we can find a number of x and y's that can satisfy this condition. For example, if you take x is equal to 5, x is equal to 5 itself, and y is equal to 0. If we take this one, so that we can find at least one x and one y satisfying this condition, so that this is true. Okay, that is all what I have for today, or simply for this video. So if you like the video, please forget just to subscribe the channel and like, comment and share this video with your friends. Thank you very much.